Okay, I think I'm on now, but I have my secret helper on the phone next to me. So maybe Thomas, you can confirm whether this is coming through.
You are live, Mads.
I'm alive and live. Excellent. So I'll go over some of the news we have in Qube version Goldcrest and the Qube 2 version Earth, and then I'll also touch upon some of the data we have generated on iPSCs on Qube as well as Qube Edge. So, as I try to illustrate here, and as Thomas already touched upon, the two instruments have a joint analyzer platform, namely the Sophion analyzer, which is sitting in the middle here, and then you have the two instruments where when you execute experiments on them, you also have commanding software for the two instruments. It's called Viewpoint for Qube, and it's called assay software for Qube Edge. But I will go through some of primarily the analyzer news, because that's where we have the biggest news. And ta-da! The biggest one of them all is this one. It's actually quite difficult to illustrate on a slide how big an event this is. We call it higher level results on lower levels. And what it means is that when you go through the analysis, those of you who are acquainted with our analysis software hopefully can follow some of this. When you go through the analysis steps, you have to go to higher and higher levels, and you didn't used to be able to go back. But now you can take any result from any level and sort of make it available to any level. There is, you could say, a risk of circular references, but that's now up to your own sort of biological and scientific responsibility, because this we have decided to allow and to thereby open a lot of possibilities. You can use it for various normalizations. Say you make a plate where you have a lot of the wells that you want to be acting as either a baseline or a reference. You could take that to the group level, and you can then take that group level result and apply all the way back to the sweep level for that matter. Very, very powerful. Also slightly difficult to sort of explain, so therefore we will urge you to get help from your application scientists, and we will also later this year, when you have had the new software for some time, we will also have some webinars where we will have specific training sessions to go through it, and hopefully also those training sessions can serve as little tutorials that we can leave on our website, so you can access them at any time. And hopefully you will just use this as much as possible. We also have other sort of more specific news in terms of what you can do in the software, and in general terms, we have actually emphasized and will continue to emphasize the fact that we would like the Sophion environment to be the only place you need to go, so to speak. Now, Thomas mentioned earlier that we also have a lot of export formats and we have a lot of connectivity, and we do that as well, of course. But as long as you don't have to, we want to give you the capability of doing every sort of analysis and even presentations within the Sophion environment as you need. That's also coming out of wishes from a lot of you guys out there, and we really worship those, so please let them come. For the so-called transform Boltzmann Fit, we actually run a 4-parameter fit. We have the Boltzmann Fit that we've always had, but now we have a new one where we have a 4-parameter fit, which actually looks into the conductance fit and not the absolute current. So if you look at this typical IV curve and you look at the asterisks, you can probably see that the asterisk on the upstroke or the downward reflecting part of the curve is not sort of geometrically in the middle of the S shape, but that's because it's actually where the conductance starts from increasing to decreasing. So that's a new midpoint you can find on such an activation part of an IV curve. We have been asked for very many years if we couldn't make an IV V curve, and now we can. We are happy to say that we can make it. So it's actually quite easy. You click on this little my symbol, and you take the group that you want to average over, and it gives you the nice relationship, as you can see in the lower left corner, where you can get the average of the currents and also the SEM error bars, as you can see here. Speaking of these averaged currents, you can also use you can appoint any sweep you like to do normalizations in this version. And small, but not the least, you can also customize the colors of your plots. We have had that since the last version on Qube, and now Qube and Qube have been even more aligned. So now you can also do that on Qube. And furthermore, maybe you noticed already on the previous slide, but you can notice that we can now make these, the way they should look, where the crossing is in 0. So the way it should look when you want to present your results from your experiments. You can even flip the graph. I don't remember exactly why this was asked for, but somebody asked for it, and we made it. And as Thomas mentioned, we have the CEPA reporting format that FDA is requiring. It has to encompass all sorts of rigs and manual patch clamp, but we have worked closely with a large group of people, and is now proud to say that we can make it very easy for you when you have to report to FDA in a format that they accept. You simply have a single button where you can either send out the whole project or selected experiments, which is entirely up to you. And speaking of a sort of another angle to satisfy authorities, if they come to you and ask for how did you record this and what did you do and when did you do and who did it, just like we have always had a traceability of who logged into our instruments and did the experiments, now we even have a project changelog and experiment changelog where you can see every smallest detail of what did what to your project at any point. It's a little bit boring, but in case you have an audit coming from the outside, it's nice for you to know that you can very easily pull up and demonstrate what was done to the experiment and the analysis. We have not had the capability of doing a single exponential fit to the IT plot on Qube, so that's another way of aligning the two platforms. So now you can also do exponential fit to IT plot on Qube, as you've been able of doing on Qube for quite some time. We are, of course, very proud of the high quality voltage clamp that we perform on our instruments. So it's actually very seldom that we have little non-perfect events, but that also makes it hard to find these non-perfect events. And if you're really going to only accept the perfect events and you want to take advantage of automatic patch clamp instruments and likewise automatic analysis, we of course need to help you out by means of software to detect little subtle irregularities. So somebody asked us to make a double peak detection. We went greedy, so it will actually be a triple peak detection, but the name was already coined at that point. So it's called double peak detection, but it will actually find up to 3 peaks of little tiny sizes on a trace, like for instance this downstroke of a sodium channel trace where you have a little bump, and of course you don't like that, so you want to maybe filter that away, and now you don't have to look for it manually, but because you can set it up automatically. Likewise, sometimes you have a little thing sticking up here, which is annoying when you do a time to peak cursor, because it would be in the old days it would be influenced by this little peak. Now you can opt to check mark this, and that's by default set to ignore little peaks like this, so you get a more clear answer, because every trained biological eye will know that this is nothing to do with the cell recording. It's just a little something, little artifact, and now the software can also recognize such artifacts and ignore them. We have had fast ligand exchange with stacked liquids for quite some time on Qube. Now I'm going to, I should mention this, I'm going a little bit away from the analysis and to the execution of the experiments. I have a few slides on that for Qube as well as Qube. So for some time it has been possible to have some fixed exchange times for the liquids. If you do the stacked liquid addition on ligand-gated experiments on Qube, that is now possible to customize entirely freely, all the way from 0.0 second up to 10 seconds. And as you can see here, as illustrated by these pipetting events, there's 0.8 second in between the wash in of the ligand and the wash out, and you can easily appreciate the downstroke here when you wash away the stimulating agent. So that's just to punch in the number that you like the channel to be exposed to the ligand in. On Qube 2, we have made it easier to detect how much liquid do you have in your cell hotel. So even though you punch in the volume over here, it's actually quite nice for the eye to easily find it at this pictogram where that depicts the cell hotel. So it will write to you how much is here at any time. You will also have a warning here that the waste container is full, and that's nice to know before you start the experiment. Of course, the experiment will be stopped for you, but still it's nice that you can empty the container before you start the experiment. And you also have a volume readout at the centrifuge telling you how much is actually being prepared in the Eppendorf tube for the experiment. It's possible now to see all in the live view on the screening station. It's possible to see all the traces in a single liquid period superposed on each other as alive as they are recorded. So you could argue that it's only entertainment, but it is quite nice entertainment to look at the experiment and to see that everything is going as expected, or if something exciting is popping up in your experiments. Adaptive protocols, where they were first invented on our instruments, we call them V-half, because that was the first obvious fraction of inactivation or activation to go for. We expanded that in version Falcon on Qube to be without limitations, and now Qube 2 is following up. So now both platforms are capable of executing what we call VXX adaptive protocols, because you can simply set the fraction of activation or inactivation of your channel in question that you want to detect online, and then use that result actively in the following either segment to stimulate with, or you can apply it to the holding potential as the in-between sweep potential that you exert your cell to. The benefit of this is illustrated here, which is real experiments. On the left panel, a range of protocols are executed in which should I say, literature-based value to obtain 20% inactivation, 40, 60, and 80% activation is applied. And you see here how much activation or inactivation do you actually get. There's a lot of biological variation. So if you instead ask the instrument, in this case it's Qube, to do a Boltzmann Fit on the fly online, estimate the Vx, and then apply that in the subsequent protocol, you can see how much tighter you get these data. When you ask for 80% availability, you get pretty much 80% of availability, 40%, etc., etc. And using that, applying that to pharmacological experiment, in this case, looking for state-dependent sodium channel blockers, you can see here the difference between, and these are data nicely done by Charles River. You can see here how running a protocol where you sort of, should we say, just use the potential that you can read, U2 should be the appropriate one, versus letting the instrument inquire the cell itself, what what does it take to bring you to the state where I'm looking for effect of my compound. You get a lot tighter pharmacological and more predictive pharmacological readout when you do it with adaptive protocol. So it's actually a very, very powerful tool to investigate your channels of interest, namely because you can put them in the state that you want to before you add the compound in question. So these were some of some examples of what's available in the new versions. There's of course a lot more to it. Some are small fixes, small news, and some are bigger ones. I've shown you some of the bigger ones in our view, at least. And these versions are available now. You can install them yourself. You will be contacted very briefly by your application scientist. You can also wait until we come to you. Thomas alluded a little bit to the restrictions we have on that still. You know all about it. Or we can send it to you. Actually, it's available for you to download, and we can help you if you allow some kind of remote access. That's entirely up to you. We hope you will install it as soon as possible and get some experience with it, and then we will have these webinars later or other training sessions so you really get to know all the details about it. And speaking of installing it, you don't need to worry about your existing protocols, whether they're being harmed by installing this. There's nothing that is being harmed by installing a new version. On the other hand, you of course don't get some of the newest features in the execution on the instrument unless you generate new protocols with the new software. But you can still use your old protocols like you've always done, just to make that clear. Okay, some data from the iPSC world. Many of you know the iPSC, but if you have a patient in this case, because that can make it even more sort of interesting. Technologies now exists, I think, since 2007 or something, where you can take somatic cells and reprogram them into becoming iPSC that you can then differentiate into whatever cell you like. And then you can use those cells for disease models and for drug screening and for cardiac safety. And applying that to automated PAT-SLAM can give you sort of the statistical power, so to speak, because you have so many experiments that even if it's still difficult to obtain high success rates, you can get substantial numbers to get a solid readout. You already heard a little bit about cardiomyocytes. We have looked into those for quite some time. In this case, you can see here some recordings from Qube 2, taking the cells, looking at whether they respond to tetracaine, indicating that there are NAV channels in them, or nifedipine, indicating that there are CAV channels. Also looking at the cell prep, how can we handle these cells so we get as high success rates as possible. And as Thomas already mentioned, they were very low in the beginning, down to very low double digit, and in this case we are up to 20%. And we have also looked into ensuring that we have actual heart cells, cardiomyocytes, so they should not be sensitive to tetrodotoxin, as you can see here. And then we have worked a lot with the conditions to handle the cells, and as you can see and appreciate over here, we are getting up to very decent, very decent success rates, where you start to get a lot of experiments out of just a single plate. So we continue to work on this. We are proud of these results, and we hope that you will also enjoy them. And we are even so lucky sometimes that we in current clam can see action potentials from some of these cardiomyocytes, and that's really thrilling. On Qube, we have looked into iPSC-derived neurons, motor neurons from two types of patients. In the first case here is the amyotrophic lateral sclerosis patient, in which case you could see the control current density, which is then increased in an ALS patient. And if you do an isogenic control, you can see that this current level can be rescued back to the normal. In this particular line of experiments, we take advantage of this 4-chamber cell transfer plate on Qube, in which you can have all 4, well, in this case, it's 2 times the control cells, and then the patient cells, and then the patient cells that have been rescued, and run those on one plate. And that gives you a lot of answers in just one experiment, since you have the 384 format. The other type of patient cells that we had access to was spinal muscular atrophy patient. Again, to control wells, and then the SMA patient cells, and then SMA cells that have been exerted to this molecule that rescues the current. Again, you can appreciate a control and the SMA, and when adding the compound to these cells, you rescue back to the normal level. The data over here that we are proudly mimicking a lot are from the literature, so that looks very nice. These data indicates very well the power of automated patch clamp on these types of cells. However, there are still some challenges with these types of cells, not so much the instrument side of it, but the cell side of it, namely the fact that the batches themselves vary a lot. So in this case, it's not a patient versus a rescued cell of some kind. It's simply batch to batch variation, and you can appreciate these n numbers. So even if there are error bars, they're very, very small and hidden in the dots. So these are actually statistically significant differences between a batch and another. So of course that makes it a little bit more difficult to be absolutely certain about the differences you see, unless you have the patient being his or her own control cell population. All these investigations we eventually turn them into reports or posters or presentations, and you can always find those on our website. So if you go to sophion.com and the Knowledge Center and Publications, you can make all sorts of filtering to do the searches. Right now we have what we call the application reports. We have 56 of those. So please don't hold back. Just go in there and find them, and you can download them. And if you have any questions coming out of reading them, we're more than happy to take those. Just contact us. So in summary, Qube Goldcrest and Qube 2 Earth are available now. We are expanding the Sophion environment to all you need, as I dare call it here. We have the higher level on lower level and many more features, and especially the higher level, lower level. I trust you will find that as a very powerful step in this new software versions. You can make the mean IV. We have a transformed Boltzmann Fit. We have extra filters to find subtleties automatically. It is, of course, still possible to export the data in many formats, for instance, the SEPA format to the FDA. And there's full traceability of who did what and when to the data analysis, so it's very easy to find out. And you can even, we also have a hierarchy, so you can control who is allowed to do what. We have an increasing amount of iPSC, cardiomyocyte, and neuronal data. And with APC platform, that gives you the high enough throughput to give statistical power. And we continue to look into the assay conditions to improve it as much as possible. And of course, we still have this batch-to-batch variability. So we are working also closely with the vendors, with the manufacturers of these iPSC cell material. So with that, I'm happy to take any questions if the technique allows. Thank you.
Lovely stuff, Mads. Great overview. I think in the interest of time, we'll try and get back on track, get Renji back on here to give his presentation. And any questions to Mads, we can hopefully take in the breakout sessions. Or, of course, he'll always be available by email, telephone, slow signal, you name it, he's on the end of it. Okay, so we will be getting Renji on hopefully soon, and we have worked out the tech difficulties, we're sure. Clearly, we're gods with our own software and hardware. but when we come to these hop-in virtual platforms, there are some learning lessons to be had. One thing I should mention actually is we won't be having our usual in-person ion channel modulation symposium at Clare College in Cambridge this year for obvious reasons. We will have a virtual one, and we hope to return to a full in-person physical version the following year. But yes, please do keep your eyes out for the virtual ICMS that will be coming up, I believe, in June.